Hey, welcome back to Fat Mama Physics. This is the third example in 6.1, Part 1, Horizontal Circles. Let's go. Woohoo! Alright. I think I'm gonna need a little bit more space. So let's see if I can try to cram everything in this tiny space here. Here we have a 0.5 kilogram mass sits on a frictionless table. So that's this guy here. So that guy is 0.5 kilos. It sits on a frictionless table and is attached through a string, so there's a string right there, to a hanging weight. Okay, so the string goes through the hole, and I'm assuming this hole is also frictionless, and nothing's going to chip the side or anything. It is attached to this hanging weight, this big M, through a hole in the middle of the table, which we're going to have to assume this is also frictionless. Anyways, the 0.5 kilogram mass is whirled in a circle. Woo! So it's going to go around in a circle of radius 0.2 meters at 2.3 meters per second. So it's going around in a circle. It's got some tangential speed here of 2.3 meters per second, while the hanging weight is dangling underneath the table without falling onto the floor. So I'm assuming this guy is not moving, okay? Alright, so now we want to calculate the tension in the string. Alright, whew, big problem. The first things first, we gotta draw a free body diagram acting on both these masses. Let's start with the hanging mass. We know this guy, there is a force due to gravity acting on him, and there's also a the force due to tension also acting on that as well. There doesn't seem to be any other forces, and also the nice thing about it is that it is not accelerating. Acceleration equals 0. I can't. No units there. Okay. The next mass is the small mass, the 0.5 kilo one. So the forces acting on this guy is, I'm going to have to use maybe orange. Okay, so this guy, we have the force due to gravity, of course. We have the normal force because this mass is sitting on a table. And we also have this force, which is directed towards the center. It's attached to a string. And that's going to provide some amount of tension force, in which this tension force acting on the small mass is going to be exactly the same tension force acting on this big mass. So that's the connection between these two objects. There is no other force acting on the M because there is no friction. And remember, since this mass you might think wants to leave the circle because it might travel too fast, remember that's not an actual force. That's the inertia of the mass wanting to leave the circle doesn't mean that there is a force doing that. So that is to be careful of. Okay, so let's, now we have the free body diagram. We can take a look at A, because all A wants is the tension in the string. The tension in the string is this Ft or this Ft connected to the small mass. But we don't really know much about, we don't know anything about this big hanging mass. We don't know the M, so we could find Ft through Fg, but we don't have Fg because we don't have the mass. We don't have the big mass. But we might know something about the small mass, because take a look at the small mass. If I have to draw a diagram of the small mass, imagine I'm drawing a view of the small mass from the side. Okay, so sure, from the side. So this small mass would look like this. And the string is tied to the middle, and then it goes through the hole, whatever. Okay, if I had to draw a free body diagram on this guy from the side view, it would look like this. So I'm just copying and pasting this free body diagram here. And the key thing about this guy is that it is moving around in a circle, meaning there must be some centripetal acceleration towards the center of the circle, in which we can write an F-net equation for. The F-net equation is going to look like this. The only force providing that centripetal acceleration is the tension force. Ooh, tension force. And we know that F-net, in this case, is your mass of the small hanging mass. Sorry, this is the small mass, small m, times the centripetal acceleration, in which we can probably find that. We also know that the centripetal acceleration is, if I write it down here, AC equals to v squared over r, in which v is the tangential speed and r is the radius of the circle. So we can rewrite this as v squared over r. And the mass here is 0.5 kilos. The speed is 2.3 meters per second. So this guy over here, 2.3, sorry, no units, it's too crowded here. And the radius, ooh, it's hiding here. Sorry, I blurred it. 0.2 meters. Oopsies. Okay, 1 second. That's going to be 0.20 meters for the radius. Okay, so if I calculate this, that's going to give me my tension force because that's the only horizontal force providing the centripetal acceleration. Okay, so that's 0.5 times 2.3 squared divided by 0.2, 13.225, which is going to round up to 13 newtons. Okay, and that's the force, that's the tension force in the string. Next one, we have B. B is calculate the mass of the hanging weight. Woo, okay. Well, guess what? Because we know the tension force now, that's Ft, and since the hanging mass isn't moving, that means that this Ft must be equal and opposite to the force due to gravity acting on this hanging mass. So if we write an equation for that, it's going to look like Ft is going to equal to Fg for the big hanging mass, in which this is going to look like 13.225 is equal to the big mass times gravity, because Fg is just mg, right? Then I divide both sides by gravity, and that's going to give me my big M. So that is 13.225 divided by 9.81. Okay, and that's going to give me 1.348 kilos. And that's going to round up to 1.3 kilograms. Woo, I fit everything. Okay, so a little bit perspective about this, about the setup here. We might get a chance to do it in class, but anyways, imagine you have a small mass. It's going to be going around in a circle, and imagine it's able to stay moving around the circle by, I don't know, something has to keep it moving. But if this mass moves around in a circle, imagine what's going to happen if this mass goes a little faster. The faster it go, that this little mass is going to want to escape the table, and this hanging mass is going to want to come up. But then if the mass goes too slowly, then it won't need as much tension force to keep it moving around in that smaller circle. So as the tension force drops, then the hanging weight is also going to go down a bit. And you can think about it if you kind of try to swing something, the more, it's like when you're trying to swing, it's like a cowboy, okay? Like you're trying to capture an animal, if you think about it. Imagine you got a rope, okay? And you're trying to swing it around to capture something, and it's tied to a big bunch of ropes here on the bottom. So the faster you swing it, the further it's able to go, and to carry all the rope that's coming from behind it. But of course, if you don't swing as fast, then, then you're not going to be able to get that. So it's kind of, there's a nice balance. There's a specific period in which, specific speed that this little m can have. Otherwise, this, the big hanging mass will not be able to stay put, okay? Very interesting setup. Okay, well, that's example 3 for you. I wish you good luck for the rest of your problems. Thank you for watching. Fan Mama Physics signing out.